Chapter 15 Physical Oceanography. What you'll learn: how scientists study oceans, how the oceans formed, and where they are located, how the physical and chemical properties of seawater differ from those of freshwater, and what causes tides, waves, and ocean currents. Why it's important. More than 71% of Earth's surface is covered by oceans. These vast bodies of water affect weather, climate, food supplies, recreation, global trade, and marine life, such as this humpback whale in Paradise Bay, Antarctica. Section 15.1 The Oceans. Since prehistoric times, people have used Earth's oceans for travel and recreation and to obtain food. Early Polynesians and Phoenicians were accomplished sailors who discovered new lands and sea routes for commerce. These seafarers acquired considerable knowledge of the oceans, but they lacked the technology to explore the ocean depths. Such exploration had to wait until the late 1800s when the British Challenger expedition became the first research ship to use relatively sophisticated measuring devices to study the oceans. Challenger also was the first expedition devoted exclusively to the scientific study of Earth's oceans, known as oceanography. The discipline of oceanography is usually considered to have started with the Challenger. Modern oceanography. The Challenger expedition investigated ocean currents and water temperature and chemical composition, seafloor sediment and topography, and marine life. The expedition used nets, bottom dredges, and other tools to gather enough research to fill 50 thick volumes. Later expeditions, such as the German research ship Meteor in the 1920s, used sonar for the first time to map the seafloor features of the South Atlantic Ocean, including the Mid-Atlantic Ridge. SONAR stands for the Sound Navigation and Ranging. It used the return time of an echo and the known velocity of sound in water to determine water depths. The velocity of sound in water is 1,500 meters per second. To determine ocean depths in a particular place, scientists send a sonar signal to the ocean floor and time its return or echo. They multiply the time by 1,500 meters per second, then divide by 2 to calculate the distance to the ocean floor. Figure 15-1 has more information about sonar. Advanced technology. Recent technological advances, such as the one shown in Figure 15-2, have tremendously expanded scientific knowledge of the oceans. Satellites such as the Topex/Poseidon continually monitor the ocean's surface temperatures, currents, and wave conditions. Submersibles, or underwater vessels, investigate the deepest ocean trenches. Large portions of the seafloor have been mapped using side-scan sonar, a technique that directs sound waves to the seafloor at an angle, so that the sides of the underwater hill and other topographic features can be mapped. You'll learn more about seafloor topography in the next chapter. For now, let's examine what all the various oceanography studies have taught. Origin of the oceans. Have you ever wondered whether Earth has always had oceans? Several geological clues indicate that oceans have existed almost since the beginning of geological history. Studies of radioactive isotopes indicate the Earth is about 4.6 billion years old. Scientists have found rocks nearly as old that formed from sediment deposited in water. Ancient lava flows are another clue. Some of these lava flows have glassy crusts that form only when molten lava is chilled rapidly underwater. Radioactive studies and lava flows offer evidence that there has been abundant water throughout Earth's geological history. Where did the water come from? Scientists hypothesize that the Earth's water could have originated from two sources. Comets, such as the one shown in Figure 15-3, travel throughout the solar system and occasionally collide with the Earth. These impacts release water, possibly enough to have filled the ocean basins over geological time. In addition, studies of meteorites, which are composed of the same material that may have formed the early planets, indicate that meteorites contain up to 0.5% water. If the early Earth contained the same percentage of water, it would have been more than sufficient for to form the early oceans. However, some mechanisms must have existed to allow the water to rise deep in Earth's interior to its surface. Scientists theorize that the mechanism was volcanism. Volcanism. During volcanic eruptions, significant quantities of gases are emitted. These volcanic gases consist mostly of water vapor and carbon dioxide. Shortly after the formation of Earth, when the young planet was much hotter than it is today, an episode of massive violent volcanism took place over the course of perhaps several hundred million years, as shown in Figure 15-4. This volcanism released huge amounts of water vapor, carbon dioxide, and other gases, which combined to form the Earth's early atmosphere. As Earth's crust cooled, the water vapor gradually condensed into the oceans. By the time the oldest known crustal rock formed some 4 billion years ago, Earth's oceans have been close to their present size. Water is still being added to the hydrosphere by volcanism. By some water molecules in the atmosphere are continually being destroyed by ultraviolet radiation from the sun. These two processes balance each other. What do you think would happen over geological time if they didn't? Distribution of Earth's water. The oceans contain 97% of the water found on Earth. Another 3% is fresh water located in the frozen ice caps of Greenland and Antarctica. In the rivers, lakes, and underground sources, the percentage of ice on Earth has varied over geological time from near zero to perhaps as much as 10% of the hydrosphere. Thus, global sea level, which is the level of the ocean's surface, has risen and fallen by hundreds of meters in response to melting ice during warm periods and expanding glaciers during ice ages. Other processes that affect sea level are tectonic forces that lift or lower portions of the seafloor. A rising seafloor causes a rise in sea level, while a sinking seafloor causes levels to drop. At present, average global sea level is slowly rising at a rate of 1 to 2 millimeters per year in response to melting glaciers. The blue planet. As shown in the image of Earth in Figure 15-5, Earth is known as the blue planet. For good reason. Approximately 71% of its surface is covered by oceans. The average depth of these oceans is 3,800 meters. Earth's land masses are like huge islands, almost entirely surrounded by water. Because most land masses are in the northern hemisphere, oceans cover only 61% of the surface there. However, 81% of the southern hemisphere is covered by water. Figure 15-6 shows the distribution of water in the northern and southern hemispheres. Note that all the oceans are really one vast interconnected body of water. They have been divided into specific oceans and seas largely because of historic and geographic considerations. Major oceans. As Figure 15-7 shows, there are three major oceans: the Pacific, the Atlantic, and the Indian. The Pacific Ocean is the largest, containing roughly half of the Earth's seawater. It is larger than all of Earth's land masses combined. The second largest ocean, the Atlantic, extends for more than 20,000 kilometers from Antarctica to the Arctic Circle. North of the Arctic Circle, the Atlantic Ocean is often referred to as the Arctic Ocean. The third largest ocean, the Indian, is located mainly in the southern hemisphere. The storm-lashed region surrounding Antarctica, south of 50 degrees south latitude, is known as the Antarctic Ocean. Sea ice. The Arctic and Antarctic oceans are covered by vast expanses of sea ice, particularly during the winter. In summer, the ice breaks up somewhat, as shown in Figure 15-8. Ice is less dense than water, so it floats. When sea ice crystals first form, a sort of ice crystal slush develops at the surface of the water. The thickening ice eventually solidifies into individual round pieces called pancake ice. Eventually, these pieces of pancake ice thicken and freeze into continuous ice cover called pack ice. In the coldest parts of the Arctic and Antarctic oceans, there is no summer thaw, and the pack ice is generally several meters thick. In the winter, the pack ice covers maybe more than 1,000 kilometers wide. Seas. Seas are smaller than oceans and are partly or mostly landlocked. The prominent example, the Aral Sea, is shown in Figure 15-9. Another example, the Mediterranean Sea, is located between Africa and Europe. It was the first sea to be explored and mapped by ancient peoples such as the Egyptians, Phoenicians, Greeks, and Romans. Notable seas in the northern hemisphere include the Gulf of Mexico, the Caribbean Sea, and the Bering Sea, which is located between Alaska and Siberia. Keep in mind that all seas and oceans belong to one global ocean, whose water are thoroughly mixed. As a result, ocean water everywhere contains nearly identical portions of dissolved salts, as you'll learn in the next section. Section 15-2, Seawater. Have you ever accidentally swallowed a gulp of seawater? If so, you've noticed its salty taste. Seawater is a solution of about 96.5% water and 3.5% dissolved salts. The most abundant salt in seawater is sodium chloride, NaCl. Other salts present in seawater are chlorides and sulfates of magnesium, potassium, and calcium. In fact, most elements on Earth are present in seawater. Because these substances are dissolved, they are in the form of ions. Table 15-1 shows the concentrations of the most important ions in the oceans. Chemical properties of seawater. Salinity is a measure of the amount of dissolved salts in seawater. Oceanographers express salinity as grams of salt per kilogram of water, or parts per thousand. The total salt content of seawater is on average 35 parts per thousand, or 3.5%. In addition to salt ions, seawater contains dissolved gases and nutrients. The dissolved gases are mostly oxygen, nitrogen, and carbon dioxide, and the dissolved nutrients are commonly nitrates, phosphates, and silicates. As you might guess, the nutrients and dissolved gases in seawater greatly affect life in the oceans. Variations in salinity. Although the average salinity of the ocean is 35 parts per thousand, actual salinities vary from place to place, as shown in Figure 15-10. In subtropical regions where rates of evaporation exceed those of precipitation, salt ions left behind by the evaporation of water molecules accumulate in the surface layer of the ocean. Their salinities may be as high as 37 parts per thousand. In equatorial regions where precipitation is abundant, salinities are lower. Even lower salinities of 32 or 33 parts per thousand occur in polar regions where seawater is diluted by melting sea ice. The lowest salinities often occur where large rivers empty into the oceans. Even though salinities vary, the relative proportion of major sea salts is always constant because all ocean water continually intermingles and is thoroughly mixed. Do the mini lab on the following page to further analyze the salinity of seawater. Sources of sea salt. Geological evidence indicates that the salinity of ancient seas was not much different from that of today's oceans. One line of evidence is based on the proportions of magnesium and in the calcium carbonate shells of some marine organisms. That proportion depends on the overall salinity of the water in which the shells form. Present-day shells show as the one shown in Figure 15-11 contain about the same proportion of magnesium as similar shells throughout geological time. Just as the proportion of sea salt has remained the same over time, so too have the sources of sea salts. In addition to water vapor, volcanic gases contain chlorine and sulfur dioxide. These gases dissolve in water and form the chlorine and sulfate ions of seawater. The weathering of crustal rocks generates most of the other abundant ions in seawater. Sodium, calcium, and potassium come from weathering of feldspars. Iron and magnesium come from the weathering of minerals and rocks rich in these elements. These ions are then flushed into rivers and transported to oceans. Removal of sea salts. Although salt ions are continuously added to seawater, the salinity of seawater does not increase. Why? Because salts are removed from the ocean at the same rate as they are added. The removal of sea salts involves several processes. Some precipitate from seawater near arid coastal regions such as the one shown in Figure 15-12. This process removes immense quantities of sodium chloride, calcium sulfate, and other sea salts. In addition, the small salt spray droplets from breaking waves are picked up by winds and deposited inland. Marine organisms also remove ions from seawater to build their shells, bones, and teeth. As these organisms die, their solid parts accumulate on the seafloor and become incorporated into the bottom sediments. All these processes remove immense quantities of salt ions from the ocean. Thus, the existing salinity of seawater represented a balance between the process that removes salts and those that add them, as shown in Figure 15-13. Physical properties of seawater. The presence of various salts cause the physical properties of seawater to be quite different from those of freshwater. Freshwater has a maximum density of 1 gram per cubic centimeter. Because salt ions are heavier than water molecules, they increase the density of water. Seawater is therefore denser than freshwater, and its density varies depending on its salinity. Temperature also affects density. Cold water is denser than warm water because of salinity and temperature variations. The density of seawater ranges from about 1.02 grams per cubic centimeter to 1.03 grams per cubic centimeter. These variations may seem small, but they are significant. They affect many organic processes, which we'll learn about in the next chapter. Variations in salinity also cause the freezing points of seawater to be somewhat lower than that of freshwater. Freshwater freezes at 0 degrees Celsius because salt ions interfere with the formations of hydrogen bonds. The freezing point of seawater is negative 2 degrees Celsius. Absorption of light. If you ever swam in a lake, you may have noticed that the intensity of light decreases with depth. The water may be clear, but the lake is deep. The bottom waters will be dark. Water absorbs light, which gives rise to another physical property of oceans. They are dark. In general, light penetrates only the upper 100 meters of seawater. Below that, depths all in the darkness. Figure 15-14 illustrates how light penetrates ocean water. Notice the red light penetrates less than the blue light. Red objects appear black below the depth of penetration of red light, and other reflecting objects in the water appear green or blue. Although some fading blue light may reach depths of a few hundred meters, light sufficient for photosynthesis is only in the top 100 meters of the ocean. Ocean layering. Ocean surface temperatures range from negative 2 degrees Celsius in polar waters to 30 degrees Celsius in equatorial regions. With the average surface temperature being 15 degrees Celsius, ocean water temperatures, however, decrease significantly with depth. Thus, deep ocean water is always cold, even in tropical oceans. Figure 15-15 shows a typical ocean temperature profile, which plots changing water temperatures with depth. Such profiles vary depending on location and season. In the temperature profile shown here, beneath roughly 100 meters, temperature decreases continuously with depth to around 4 degrees Celsius at 1 kilometer. The dark waters below 1 kilometer have fairly uniform temperatures of less than 4 degrees Celsius. Based on temperature variation, the oceans can be divided into 3 layers, as shown in Figure 15-16. The first is relatively warm, sunlit surface layer, some 100 meters thick. Under this is a transitional layer known as the thermocline, which is characterized by rapidly decreasing temperatures with depth. The bottom layer is cold and dark with temperatures near freezing. Both the thermocline and the warm surface layer are absent in polar seas, where water temperature are cold from top to bottom. In general, ocean layering is caused by density differences. Because cold water is more dense than warm water, cold water sinks to the bottom, while less dense, warm water is found near the ocean surface.